Hi everyone, welcome to the ninth lecture of the series on sliding mode control. In this lecture, we will discuss about nested or sliding controller, which is basically a higher order sliding mode control approach. Here is the overview. We start with the nested 2 sliding mode controller, which is a second order sliding mode controller. Then we move on to the nested R sliding controller, which is the arbitrary order higher order sliding mode controller. Nested 2 sliding controller is a second order sliding mode control approach and can be applied to nonlinear systems of form as in equation number 1, and we select the sliding variable as in equation number 2. For second order SMC, we have the control input u should appear in the second derivative of the sliding variable s. In that case, we can represent s double dot as in equation number 3, where a of tx and v of tx are unknown terms which are assumed to be bounded. So here u appears in the second derivative of the sliding variable. Therefore, using the control input u, we can make both s and s dot 0. And for that, we can use the nested 2 sliding controller, for which the general form is given as in equation number 4, where alpha is the switching gain. Here we have two signal functions, and this part we can call as the switching function, and by equating this to 0 we can obtain the sliding surface dynamics as in equation number 5. Here we can also introduce a constant name beta, and in this case we are considering beta is equal to 1. In the control law we can define the time sigma as in equation number 6. So in the previous control law we selected beta is equal to 1, but beta can be chosen as any positive scalar. Now if we take the derivative of this term, we have s double dot appears, and in which we can substitute the differential inclusion, and which results in equation number 7. Now for sigma equal to 0, we have s dot equal to minus beta into mod s raised to 1 by 2 sigma of s. Now if we substitute this s dot in this equation, we can rewrite it as in equation number 8. Now in order to ensure sliding mode at this surface, we have to ensure that sigma dot less than 0. And if we use this here and rearrange the terms, we can obtain the criteria for switching gain as in equation number 10. This gives a criteria for selecting the switching gain based on the uncertainty bounds. So here km and c are the bounds of the uncertain terms, and beta is a parameter chosen in the switching function. Based on these parameters, we can decide the switching gain as per this criteria for ensuring stability. Next, we consider the simulation of nested 2 SMC, and for that we consider a simple pendulum system as given in equation number 11. The sliding variable is chosen as the output error, where r is the reference value, and we select the nested 2 SMC controller as in equation number 12, where the switching gain is chosen as 10. Now in order to implement this control law, we require the estimate of s dot, and for that we can use a sliding mode differentiator as defined in equation number 13. The simulation parameters are chosen as in equation number 14. Now this figure shows the plot of s versus s dot for the nested 2 SMC, and here we can see that both s and s dot are converging to 0, starting from some non-zero initial values. And this plot shows the response of the simple pendulum system with the nested 2 SMC. Here we can see that the actual state value is converging towards the reference value, and the sliding variable is converging to 0, which means that the output error is converging to 0. And this shows the plot of s dot, which is also converging to 0. And finally here we can see the control signal. Next, we move on to the nested R sliding controller, which is basically the arbitrary order sliding mode controller. For that, we consider the nonlinear system as in equation number 15, and the sliding variable is chosen as the output error. So here we are considering a higher order sliding mode controller with arbitrary order, and the order is considered as R. Now this rth order sliding mode controller can be used if the control input u appears in the rth derivative of the sliding variable s. In that case, we can represent the rth order derivative of the sliding variable as in equation number 17, where a and b are the unknown terms for which the bounds are as given in equation number 18. Here the control input u appears in the rth derivative of the sliding variable. Therefore, by properly designing the control input u, we can make the sliding variable as 0. So if we use these bounds in this equation, we can rewrite it as a differential inclusion as given in equation number 19. And our objective is to design a controller u which can stabilize this differential inclusion. And one such controller is the homogeneous R sliding controller, which is as given in equation number 20. Here alpha is the switching gain and phi is the switching function, which can be defined recursively as in equation number 21. So we can show that this differential inclusion with this R sliding controller can ensure finite time stability of the system. This means that we can make the sliding variable or the output error 0 in finite time using this R sliding controller. Now from this general equation, we can obtain the R sliding controller for relative degree 1, 2 and 3 respectively as in equation number 22. Here we can see that the switching gain alpha is the only design parameter which can be selected based on the uncertainty bounds, which are C, K1 and K2. We can also see that in order to implement the R sliding controller, we require R minus 1th order differentiator for estimating the derivatives of the sliding variable. Therefore, next we move on to the sliding mode differentiator, and this is the general form of a rth order sliding mode differentiator. Here this alpha 1 to alpha r are chosen using this equation, and these parameters lambda r minus 1 to lambda 0 are chosen as positive constants. Now if we select these gains properly, we can ensure finite time estimate of the sliding variable and its derivatives. And the estimated value of the sliding variable and its derivatives can be used for implementing the R sliding controller. Next, we consider the simulation of nested R sliding controller. For that, we consider a third order system as given in equation number 25. The sliding variable is chosen as the output error, where R is the output reference and X1 is the actual output. And we use the nested 3 sliding controller as given in equation number 26. Now, in order to implement this nested sliding controller, we use a second order differentiator as given in equation number 27, which basically estimate S double dot and S dot. The simulation parameters are chosen as here. And this plot shows the response of the third order system with the nested 3 sliding controller. Here we can see that the actual output is converging to the reference output, and the sliding variable and its derivatives are converging to 0. And finally, here we can see the control signal. The Matlab course for this simulation can be downloaded from the link given in the description. That completes this lecture. Thanks for listening.